Welcome back. Now we're on assignment 3, which is working out of chapter 2, section 1. Here's where we begin to consider some of the big ideas of calculus. I've got a graph that you see, and this graph is showing you the position of a particle of a car as we change time versus the position of the car. If I ask you for the average speed of the car between the two times t and t plus h, well, the average speed will simply be given by this expression. Average speed is equal to s of t plus h minus s of t all over h. And what we notice is pretty simple, is that what we have just defined is the slope of that secant line that goes between the 2 points of interest. That's the average speed between two discrete times. Suppose we want to know the instantaneous. Instantaneous speed at t. What we see is what we want to do is let this point get closer and closer and closer to t. And so the instantaneous speed at t is going to be, as we wrote above, s of t plus h minus s of t over h, and now we take the limit as h goes to 0 of that. So let's formalize these ideas a little bit. If we have any curve at all, and we connect two distinct points on the curve, we have what's called a secant line. If we let one of those points get arbitrarily close to the other point, then we get what is called a tangent line. If I call this point P and this point Q, then here is the way we define tangent line. The tangent line at P is the limit as Q approaches P of the line PQ. And understand that in this idea of a limit, Q gets very, very close to P, but Q never will equal P. So we have an idea of a secant line, and we have an idea of a tangent line, and finally we have the big idea of calculus, which is that the derivative of f at the point P is simply the slope of the tangent line at P. We have a lot of ways to express the derivative. If I have a function f of x, one of the ways to talk about the derivative is f prime of x. And f prime of x is defined as follows. Remember, the derivative is the slope of the tangent line. This is going to be the slope of a secant line between points x f of x and x plus h f of x plus h. So to make that secant line be a tangent line, we simply take the limit as h goes to 0. And this is one of the most important ideas that we have in all of calculus, the definition of the derivative. And what we can do is simply indicate that by writing right above here that this is the definition of the derivative. So let's formalize a little bit more exactly what we mean by a limit. If I write the limit as x approaches a of f of x equals L, what that means is as x gets close to a, f of x gets close to L. And remember, with all ideas of limits, we're talking about what happens as x gets close to a, but never equals a. At this point, I urge you to pay attention to Theorem 1 and Theorem 2 in our textbook. And they will give you a list of properties of limits that I won't take the time to discuss here. So let's learn a little bit more about the idea of limits with these three pictures that we have. In each case, there's something important to be learned. In the first case, the limit as x approaches a of f of x does indeed equal L. As x gets close to a, f of x gets close to L. The fact that the function f of x is not defined at a doesn't matter at all, because remember, we don't care what happens at a. In this next case, we have the same thing. The limit as x approaches a of this function f of x again is equal to L. And the fact is that even though this function is not defined to be L at a, it's defined to be m, we don't care what happens as x gets close to a. The last one is the more interesting one. In this case, the limit as x approaches a of f of x does not exist. And the reason is, as we get really close to a from the left, f of x is getting close to L, and as we get really close to a from the right, f of x is getting close to m. So this function, although it does not have a limit at a, it has what we call a left-hand limit and a right-hand limit, and I indicate that with the following notation. The limit as x approaches a from the left of f of x is equal to L, and the limit as x approaches a from the right of f of x is equal to m. And since L and m are not equal, that's why we say this function does not have a limit at a.